And welcome back, future physicists. Today we're looking at a very basic projectile problem about a Coast Guard plane flying horizontally, and that horizontally is one of the big words in the problem, with a speed of 50 meters per second. It also gives us a height off the ground. So let's just look at a basic projectile problem. So the most basic projectile problem is one that kind of, wow, that was horrifically bad. Let's see if we can't draw better than that. Uh, the most basic projectile is this. Wow, still not a whole lot better, right? The most basic projectile problem is when you've got a pretty simple parabola. And what's cool about this problem, it starts us at the very peak of the parabola. So when we're looking at this, here's the thing we always know. We're always concerned about our velocity y and our velocity x when it comes to projectile. What's neat is this: when we are at the top of this arc, the thing is not moving up or moving down for like that brief moment. And that lets us know that our velocity at the peak is 0 meters per second. Well, that's exactly what we've got going on over here. When we see this Coast Guard problem, what's neat about it is this. We know we have a velocity initial, x, and everything's about X and Y, remember. We know we've got one of 50 meters per second, but we also know something else. It doesn't tell us this, but since this thing is flying horizontally, it's also letting me know their velocity initial Y is 0 meters per second. Now, I'm going to do one other thing. It's told me like a Y value here of 120 meters. I'm going to be a little bit more nitpicky. I'm going to say my Y initial point is 0. And I always do this. Wherever I start the problem, I make that my 0 point. It actually makes the math easier, especially when you get to harder problems. Now, when you get down to the bottom, I'm going to call this my y final, and I'm going to make that negative 120 meters because I'm going to end up 120 meters below where I started. Everything, if you remember everything in the projectile problem, what we're always concerned with, boom. Ah, hey, how come you didn't go away? Get out of here. Everything in a projectile problem is always concerned with your displacement values. So let's do this. This problem asks us how far horizontally did it go. You know the cool thing about a projectile problem? We went over this in our notes. The only equation we have for x in a projectile problem is x equals voxt. There's just one catch. We don't know the time so that we can plug it in here. But what's cool is this. My go-to equation for time in a projectile, delta y, is equal to v so y t plus 1 half at squared. Now, here's the only thing you're going to notice difference. Most books are going to write it like this. Equals v so y t minus 1 half gt squared. Now, these are the same equation. If you use the 1 half at squared, all I'm going to do is I'm going to use a value of negative 9.8 meters per second square for my acceleration. Whereas if you use this equation, you just use regular 9.8 because the negative is already taken into account of. Hey, either equation you use is going to be beautiful. You want to know why? Because VOY, boom, it's 0. It had no vertical component. My change in y is negative 120 meters equals, and now look at this, negative 1 half g is 9.8 t squared. So this ends up negative 120 meters equals negative, why am I still writing negative, right? T squared. And let's see if we can get a little calculator or something going here at this point. We got what? 120. Of course, negatives will cancel. Divide that by 4.9. Now, I'm still not done because this is 24.5. So I know 24.5 is equal to t squared, which means I still need to do one more step. I need to take a radical, take the square root of both sides of that. So let's see if we can't grab hold of that. Radical of that answer is 4.95. So my final answer, now I know that time is 4.95 seconds. So if I want to know how far this thing travels at this point, it's pretty easy. X is equal to, and for the sake of our math, let's just round that number off. 50 in here. For somebody that's concerned about units, I'll write the units on this because it's pretty simple. Times, that's basically 5 seconds, guys. The seconds cancel out, and we are left with 250 meters, pretty roughly anyway. So there's how we found our X. If we want to find the second question, it says, what are the horizontal and vertical components of the raft velocity before it strikes the water? So let's take a look at this point. Right before the thing hits the water, it's going to have two velocities. It's going to have an x velocity and it's going to have a y velocity. Now, sometimes a question will even ask you to find like just the velocity. If it says that, all you've got to do is take the Pythagorean of your x and y values. So that's pretty easy. What's neat is I already know my velocity x because this is a projectile, and unless you've got air resistance, this x velocity never changes through the flight, which means even by the time we get down here, the velocity of this thing is still 50 meters per second. Well, that's easy. So now it just becomes a question of how do we find our y velocity? Well, we've got two ways we could do it. I'm actually just going to do this, VY minus GT. You could also use plus AT, just of course substitute in there your negative 9.8 at that point. So here's what we got. Vy equals, I know V sub OY is 0, minus G, which is 9.8, times 5 seconds for our time. And boom, look at this. Man, if we're in AP, oh, I'd love it. Let's do it AP style. If we're in AP physics, we can just use a value of 10 for that. So we've got a velocity of negative 50 meters per second. And the negative is important because that does show the direction of this object. The velocity x, of course, is still there. And hey, guys, you got it. You have just solved an awesome projectile problem. Hope you guys have fun, great days, all that other stuff. Bye.